All right, thank you. So I'm glad to present our paper, which is Human AI Collaboration with Misaligned Preferences. And my name is Jiaxin, and this is a joint work with my amazing co-authors, Parnian, Kate, and Bhaskar. So today I'm just first talk about the motivation behind this model. So nowadays we know that algorithm is widely used for humans decision making. Like machine learning models is widely used for prediction, and optimization skills are widely used for transportation. However, because of the different information that they have, so usually they have different abilities and advantages. So one question here is that when will the human get benefit from the collaboration? So before talking about the collaboration model, I will first talk about the motivating example, and it's about myself. So when I first got to Pittsburgh, I want to find the route from my hotel to the conference hall, and then I asked Google Map to give me some options, and then it provided me 4 routes, and then I pick one that is my favorite. But I'm not familiar with Pittsburgh, so this one may not be always be my favorite one. So here Google Map is like a curator, and it has some ordering about all the routes, and it depends on the underlying optimization algorithm of Google Map. And it presents a subset of all the routes. Let's say it's k routes, and it's smaller than total number of routes. And the human just randomly pick one of this, and yeah. So there is also another set of motivating examples, and we just lead as follows. So now I just move our focus to the formalization of a model. So there is a set of alternatives, and there are two actors. One is algorithm, another is a human. And both of them have the preference ranking and pay star and page star. However, in reality, we know that each of them can make some mistakes. So we assume that both of the two actors are noisy. So they are like pay and page, but they just satisfy a distribution, and pay and page may not always be the same as their true preferences. So our model is basically based on a generalized model, but it can also cover some specific model like Malus model and Placius model. And the goal of the human is just to pick one good alternative. So now, yeah, so when the human is working alone in this figure, in the right figure, if her preference is like 2, 1, 3, then she's just picking the top item in this ranking. However, if she's working with a curator, like we have shown in this motivating example, the AI will first narrow down this entire set into a subset. Like here, it will just choose two items from from the overall set, like 3 and 1, and present these 2 items to the human. And within these 2 items, the human will just pick the one that is her favorite one. So like here, because 1 is her favorite one, so she will just go with item 1. So the question here is that how do we evaluate the performance of a collaboration model? So one solution is complementarity, and which is defined as the stress system is better than either of the human and the algorithm. So one question is that when do complementarity hold? And by a previous work by Donahue et al. And result of our work, we show that when these two patterns are the same, it's like when the human and algorithm have the same preferences, we find complementarity always hold if they are equal accurate. However, we know that the real world is much more complicated, so it may not always be the case that the persons are the same. So they are usually their preferences are different. So the question is that do people still get benefit when the preference ranking are different? And our answer is yes. And sometimes misalignment is more helpful than alignment algorithm. So I will start with a toy example to show the benefits of a misaligned AI. And I find this toy example very helpful to give some intuition. Like here, there is one human, and Alice has a person ranking like X1, X2, X3. And but she also makes some mistakes. So there is 19% that she will identify her true preference, but there will also be a 10% that she will make some mistakes by swapping these two top items, X2 and X1. So when she's just making decision alone, So she has a 10% to mistaking the suboptimal item X2. But here we're considering that she's working with a misaligned AI, whose ground truth is X1, X3, X2. It's different from her preference ranking. But surprisingly, we can find if the algorithm is presenting top two items, X1 and X3, to the human, Alice will always pick the top item X1. This is because that she is always able to distinguish these two items X1 and X3. So we can find when working with a misaligned AI, she's always able to pick the top item, but when she's working with a aligned AI or working with alone, she may not always be able to pick her top item. So our first set of result is that when there is one human and there is a set of algorithms, and some of algorithm may be misaligned to the human's preference, and some of algorithm may align to the human's algorithm. So our question is that which one is a good one and which one is bad one? And we focus on a special case, and we call it the top item recovery. So in this case, the human only values the top item. So there is just one valuable item to the human, and all the other items are not valueless to the human. And our result is like in this setting, we find any misalignment between this biased item and other suboptimal item will hurt the human. But any misalignment between other items will always be beneficial to the human. Yeah, so as the implementation, we find the biased AI is just like put the top item at first and then reverse all the other items. So we found this is also intuitive because in order to help the human to identify the biased item, so I should try to distinguish the top item from other items and also help human to distinguish these things. So we also consider about generalized setting, which is called beyond top item recovery. So here, human also has some value to the other items. And we generalize our theorem, and it's like in this general setting, we find any misalignment between these top items will be harmful to the human, but any misalignment between the items that are far from optimal will be helpful. Yes. So our second set result is about now we suppose that there is just one AI, and there is a population of humans, and the goal of the AI is try to optimize the welfare function. And basically, there are just two welfare objectives. One is the AI is trying to maximize the total utility and social welfare. And the other one is that the AI is trying to guarantee all the agents all the humans are get benefit from the collaboration. We find, unfortunately, these two objectives are both hard to optimize in general. But we find there are some special cases that we can solve it efficiently. And also, as a special case, we find for the first welfare function, the social welfare, we find zero noise is always optimal. Like the algorithm should always try to minimize the noise. But for the second case, we find small noise sometimes can be helpful to achieve uplift. So in the last section, I want to talk about the empirical study and which about the sushi. And these photos are taken by the restaurant at Pittsburgh. Okay, so suppose you are ordering sushi and you have some preferences over all the sushi, but you have some noise in making your decision. And there are also other people coming in this restaurant. So at a restaurant, so how do you design a menu to satisfy all the preferences of these humans? And we are considered about limiting case. So we assume that the humans are not perfect in making their decision, because if they are performing perfectly, there is no point to design algorithms. So we are considering about three algorithms. One is just trying to maximize the total welfare, and the other is trying to maximize the percentage of uplift. And the last one is about just following with the majority of these humans. So in this first figure, in the last figure, we find these three algorithms perform almost the same in maximizing the in terms of the social welfare. And the one that maximizes total social welfare is slightly better than the other two. But if we consider about the uplift, we find if the algorithm is trying to maximize the social welfare, then about half the human will get hurt in the collaboration. And the open question is that, so in this exercise, what is the general trade-off between these two welfare functions? And yeah, in all empirical study, you find the maximizing the uplift will be better than just maximizing the total social welfare. But what would be a general trade-off between these two things? And next, I'll just give a summary. So the takeaway is that we find misalignment can sometimes be helpful, but yeah, but sometimes may not always be true. And also the complementarity comes from that the different types of errors that human and organism makes. And some future work is like some generalized definition of misalignment, and also some formalization about the knowledge level of the human and organism beyond this distribution, and also like some trade-off between these welfare objectives. So any questions? Thank you for listening.
Questions? Questions from the audience? I have a question. So you said in your second result, noise harms utility, but helps uplift. Can you give us some intuition?
Yeah. So that's a good question. So it's like in all this SCR, it's a very large majority of humans that they have the same preference. So if you just try to maximize the social welfare, so the solution is just try to align with the majority, but they may hurt some minor groups of this humans. So yeah, so that's why we need some randomness. So if you add some noise to the algorithm, so if you add some randomization, it also allows some minor groups can also has a chance to pick her favorite ones.
Okay, if there are no questions, let's thank you again.
Thank you.